Hello, this is Mr. Mario with Noteworthy Science. Today we'll be doing the additional higher level components of subtopic A1.1 Water. Under the curriculum matrix, this falls under theme A, Unity and Diversity, and under the level of organization of 1, Molecules. So in the additional higher level component, a key understanding is kind of expressed by the very first guiding question, which is what physical and chemical properties of water make it essential for life? And that is really the core of what we'll be exploring in an additional higher level. While there are only 2 learning outcomes in higher level, I find these 2 learning outcomes among some of the coolest in this entire course. And it's really talking about why is it that we look for water when we look for life outside of Earth? And really, why is water on Earth in the first place? What was the origin of water on Earth? These are questions that we're still trying to explore. So we'll be going over a lot of hypotheses that are currently being put forward to answer these really important questions. It's really the search for life and what role water has in this question. Let's begin. Here, so far in standard level, the whole point of this subtopic was really, why is water so vital, so necessary for life, right? That's kind of like the too long didn't read statement of this entire subtopic. The HL component, I think, is extremely interesting because it's now taking that in a step further, which is, 1, how did water get here in the first place? i.e., what's the origin of water on Earth? And the second main thing that we're going to explore is, if water is so important to life, we're going to be discussing how do we look for water in other planets, and we can use this as a way of maybe gauging if life actually exists outside of Earth. We know life as we know it requires water, so if we look for water, there's maybe a chance that life is also there. So that's what this whole topic is going to be all about. So something that we've briefly alluded to in SL is early Earth. And early Earth was really, really chaotic. In fact, this is the first era. So Earth was formed roughly 4.6, 4.7 billion years ago. And around that time, it was really chaotic. Things were still forming. There was asteroids everywhere. There was a lot, very, very high temperatures, high volcanic activity. In fact, it was so crazy that the name of the era is the Hadean era, which is named after Hades, i.e. hell. So it was a really chaotic time. And so early Earth was really, really hot. Now the reason that I'm mentioning this is because if we assume that early Earth had water in the first place, like that's the origin of water, it's extremely unlikely that water stayed during this time. Because it was so hot, almost certainly water would have evaporated, and we would have lost water to space. So for this reason, or this is a large reason why we believe that water almost certainly has an extraplanetary origin, meaning that it has an origin outside of Earth, meaning it came from elsewhere. So this is a great example of somewhere in the course where I think a lot of people assume that when they learn in a science course, they assume maybe that we've already figured everything out. But that's not true at all. This is a really good example of we are still not sure. And this is for this reason I'm using the term not a theory, I'm using a hypothesis. In fact, there are still competing hypotheses for the origin of water on Earth. We're going to be discussing today the most prominent or the most accepted hypothesis right now. And that is the leading hypothesis of water's origin is from asteroids. So before I go into this a little bit, this is not super important for this topic, but I just thought it would be worth going over a few definitions because these terms get, I think, confused or used interchangeably all the time, and I just wanted to just do a quick recap here. So if there's a huge rock body orbiting the sun, and there's thousands of these in our solar system, we call those asteroids. I mean, there's even an asteroid belt, right, in our solar system. A meteoroid is a fragment or a small part of a rock that's also there. And then finally, when that fragment actually enters our atmosphere, we call that a meteor. In fact, if you actually can see this, if it's starting to burn up in our atmosphere, we use the term a shooting star. That's what that is, right? You see that flash there? That's a meteor burning up in our atmosphere. If it actually makes it to the surface of the Earth and actually lands, we call that a meteorite. These terms aren't like super crucial for this course, but I think people often confuse these terms and I just kind of wanted to include it. So the hypothesis here is that these asteroids contained water, and some of them ultimately landed on Earth and delivered them. Now, it may seem a little odd, this hypothesis may seem a little far-fetched in the sense that wouldn't all that water also have just evaporated? What's actually holding water there? And we believe that the water actually was contained within these crystals, or these hydrated crystals. And that's what actually allowed water to arrive on Earth. And the other question might be, is it really likely that there was these impacts? You'd have to have a lot of water delivered, and right now there's very few impacts happening on Earth. But again, in early Earth, during the Hadean era and the eras afterwards, there was an enormous amount of collisions. So there would be a lot of opportunity for water to be delivered in this way. Now, the question becomes, what evidence do we have to support this? If we're going to have a hypothesis, then we're going to need to support that with some evidence. And the evidence that we're going to be using actually comes from isotopes. So as a revision from chemistry, an isotope is any element that has the same number of protons but different number of neutrons, meaning that it has the same chemical properties but it's going to have a different mass. And we'll be using isotopes a lot throughout this course. It's a way that biologists can actually track the origin of certain chemicals, even at a really, really, really small level. And in this case, we're going to be looking at the isotopes of hydrogen. The most common form of hydrogen is called hydrogen 1 or protium, and that has a single proton, no neutrons, and 1 electron. So it would have a relative atomic mass of 1. Whereas a more rare isotope, but also naturally occurring isotope of hydrogen, actually has 2 subatomic particles in its nucleus, 1 proton and 1 neutron, called deuterium. So this would have a relative atomic mass of 2, right? And that's why if you look at the periodic table, the mass of hydrogen is not listed as 1, it's 1.01, because there's still a little bit of deuterium, which is causing its average to increase slightly, right? So specifically, where are we looking for this hydrogen isotope? Well, we're looking at it in water, because water can be formed using either protium or deuterium. So as you can imagine, because this isotope is significantly more common, the most common form of water, or normal water, would contain protium with oxygen. And that's why typically the mass of water would be 18.02, which is 16, 1.01, 1.01 for that mass. However, there is some water that would be formed not using protium, but deuterium. And in that case, water would actually have a larger mass. And that's why colloquially, sometimes it's called heavy water. So that's what heavy water means. It's atomically heavier because it contains a heavier isotope of hydrogen. Now, both normal water and heavy water both naturally exist on Earth. This at a significantly higher ratio than this, but that ratio can be determined. In fact, we can determine the ratio of isotopes in any body by using something called laser spectroscopy, which is we can actually shine a laser through a material and then we can determine different absorbances based off their isotopes. So when we did this technique in our oceans, we can actually determine the ratio of normal water to heavy water. And what we've done is we compared that naturally occurring ratio to the ratio of normal water to heavy water in these hydrated minerals. And what we found is that it is extremely similar, like very, 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 very similar. So the ratio of these isotopes found in our oceans was found to be extremely similar to the ratio of isotopes in asteroids. And so for that reason, it's a very strong piece of evidence to suggest that these are likely the origin of this water in the first place. It would be incredibly unlikely for the exact same isotope ratio to exist just haphazardly. So it's for this reason, it's not definitive proof, right? We have to look at likelihood. And in this case, it's a very strong piece of evidence to support the idea that this is where water came from. This is where water was delivered, were from asteroids. This first learning outcome is looking at what is the hypothesized origin of water on Earth. And in this case, widely supported or a strongly supported hypothesis would be the asteroid hypothesis, meaning that water's origin on Earth is actually extraplanetary. The next learning outcome here is talking about, okay, we now have an idea of how water was delivered to Earth in the first place. The next learning outcome is going to be, how did water stay? How did water remain on Earth after it's been delivered? And there's a few elements, or there's a few factors that we have to consider here when that's the case. So first of all, a factor to consider is the size of the planet. And that has to do with, and that's going to determine its gravitational pull. So, quick question, what is the relationship between the size of a planet and gravitational pull? Correct, the larger the mass of the object, right? It means it would be, well, slightly bending space-time a little bit more than, let's say, a lighter object, right? And that means that there'd be a larger gravitational pull, right? So that's why, like, my mass, if I go from here on Earth to the moon, my mass should be the same, but my weight will not be. Because the moon is so much smaller than Earth, the gravitational pull is much weaker, meaning that my weight is actually much less. Right? And vice versa. So the larger the planet is, the larger the body is, the greater the pull. So this means that a planet, in order to retain water, needs to be large enough, with a large enough gravitational pull, to actually hold liquid water on the surface and actually keep it from going away into space. So that's one factor to consider. And Earth's gravitational pull, as we are well aware, is large enough that it holds liquid water on the surface. Now, another factor really has to do with a planet's proximity to its star. So the idea here is, and remember, our sun is really just a star. We've named it the sun, but it is just a star. The proximity, or how close a planet is to its star, will actually change its temperature, right? So the closer a planet is to a star, the warmer it will be. The further a planet is from its star, the colder it will be. And so what we're caring about here is that we know, or at least as far as we know, life requires liquid water. So we have to find the zone in a solar system where a planet has a temperature that allows for liquid water. So that means if the planet's temperature was too hot, it would evaporate as a gas, and liquid water would not be possible. And if the planet was too far, it would be too cold and would only be found as ice. So this zone is something called the Goldilocks zone. Goldilocks, after the classic story of Goldilocks and the Three Bears, where she enters a home and then tries, let's say, porridge that was too hot, porridge that was too cold, but then finally there was porridge that was just right. So the idea here is that we need to find a zone that is not too hot and therefore water vapor, too cold and therefore ice. We need to find the zone that is just right for liquid water. And this is what we call the Goldilocks zone. Now, in our solar system, with our star, the only planets in that Goldilocks zone is Earth and Mars. Planets beyond Mars are too cold. Water, it would only be found as ice. And planets too close, such as Mercury and Venus, would be too hot, and that would only be found as water vapor. Now, there's another factor to consider. If we're looking for the Goldilocks zone in other solar systems, stars vary in size. So the next question I want to ask you is, how would the Goldilocks zone differ with the size of the star? If the star got larger, then the Goldilocks zone would have to be shifted further and further away because it's emitting so much more energy, and therefore the proximity would have to be further out. But if the star was smaller, it would have to be closer and closer to the star because it's emitting less energy. So taken all together, when we look for the Goldilocks zone, and we're really looking for, can this planet support liquid water? Does it have a sufficient gravitational pull to actually hold on to it? Is its proximity to its star such that liquid water is possible, meaning that the temperatures are within liquid water's range, so above 0, below 100 degrees Celsius. And this idea here is fundamental to a field of biology called astrobiology, or the search or the study of life outside of Earth. Really, these two ideas go hand in hand because our whole hypothesis for life is that we need liquid water. So if we're looking for liquid water, there may be a chance that life is also there. So astrobiologists are effectively looking across the galaxy for potential candidates for life, i.e., which planets are in their Goldilocks zone of their star? And that's what we're looking for. That's where these candidate planets come in. Now, there's something else also to consider, and that is, what's its atmosphere like? Because it's one thing for a planet to have sufficient conditions for liquid water, but what about its atmosphere? And just as a recap, the atmosphere just means a collection of gases surrounding a planet, right? So how can we identify the composition of the atmosphere light years away? How can we do this? Well, believe it or not, we can using a technique called transit spectroscopy. And in this case, how it works is that you have a star that's emitting energy, and as a planet passes in front of that star, it's causing almost like a shadow in how much energy is being emitted. We're trying to detect the absorbance through a gas layer. And something like oxygen versus water versus carbon dioxide are all going to have slightly different absorbances. So when we analyze the absorbance of that through the layer, we can determine, is there carbon dioxide? How much carbon dioxide? Is there water? How much water? So taking all of this together, we can see, is water actually present, yes or no? So it's almost like the stage of, if I'm an astrobiologist, what's my order of trying to find life on another planet? One, I'm going to try to identify where's the Goldilocks zone. Once I've identified candidate planets in that Goldilocks zone, I'm then going to try to use spectroscopy to determine, is water actually present in the atmosphere? If that's a second yes, this planet now becomes fairly likely at potentially containing liquid water on that planet. And thus, it's a candidate for potential life in the galaxy. We've found hundreds of candidate planets already. So the question is, why? Why haven't we found any life yet? And there's a lot of factors to consider. The other thing, I think a factor that I'll just say right now in terms of maybe trying to answer that question a little bit is time, right? So let's think of Earth as for a second. If another species and somewhere else in the universe looked at Earth 2 billion years ago, what would they have found? They wouldn't have found much unless they were able to even look into microscopic life in the oceans. They would have seen nothing on the surface of the planet. In fact, you wouldn't have seen civilization if you looked back 20,000 years ago, 30,000 years ago. So it's not just, does this planet have life? It also kind of matters when you're observing it. Because even our own planet, complex life has not been around that long, especially when you consider how old the Earth is. So that is a factor to consider, right? And another cool thing about physics too is the further away you look in the universe, the more back in time you're looking, right? It's like a weird, it sounds really odd to think about, but like the light that we're getting from the sun right now is 8 minutes old, because that's how long it took for that light to reach us. So the further and further and further back you look, it's almost like you're looking back in time, really. Like so many stars that you're looking up into in the sky aren't there anymore. It just took that long for the light to reach us. So it's kind of astrobiology and astrophysics is such a cool area to really examine, and this is just kind of a brief taste as to what's water's importance in this whole idea. Let's review the learning outcomes for additional higher level for subtopic A1.1 Water. In higher level, there are 2 learning outcomes that we've explored. Specifically, the first one has to do with what exactly is the origin or the hypothesized origin of water on Earth. And in this one, we've explored the hypothesis that it had an extraplanetary origin, meaning outside of Earth. Specifically, we're referring to the hypothesis that Earth's water originated from asteroids, and what exactly is required for water to have remained on Earth. And secondly, this learning outcome is all to do with water's relevancy in looking for life outside of Earth, and why water is so necessary and why it's a really good step to look for life outside of our planet and outside of our galaxy. And the key concept here is that of the Goldilocks zone, and how this helps inform scientists as to where to look for life outside of this planet. If you want to learn further, which I always encourage, this final page is a good place to start. Here are textbooks that I've used to help develop these lessons, and specifically what page numbers are relevant if you'd also like to read. Underneath are simulators that really help explore further the concepts that we've studied in this topic, and this really provides a more hands-on experience at exploring concepts like polarity, hydrogen bonding, surface tension, and specific heat. The 3D models really help explore molecules, well, like it says, in 3D space, and it really gives you a better sense as to how ice forms sheets and how liquid water interacts with itself. Finally, these articles are really nice places to do further reading, specifically about the roles that water has in terms of biology and in living systems, and its relevancy in looking for life outside of the planet. Finally, I would always encourage students not just to learn for the sake of a test, but learn for the sake of learning, learn for enjoyment.